Hey everyone. So looks like this question is asking us to draw a velocity time graph for the position time graph representing the motion of the ladybug. So here's our position time graph, and it looks like this ladybug here started at 0, and then it took 5 seconds. It took 5 seconds for this ladybug to move up to position 5. So it moved right to position 5 right here. And then it stayed there, it chilled for a little bit, and then it moved back to position 0. So now let's try to draw our velocity time graph next to this. So what was our velocity time graph look like? So make a graph like this. V and T. Meters per second, seconds. All right, so it looks like there was a total of about 13 seconds on this graph, so I'm going to draw 13 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Perfect. So first off, remember that using our AVX diagram, so we write A, V, X, and then when we go up it, we write slope, and when we go down, we write area. So we start with what kind of graph we have. So we have a position graph, so that's an X graph. This is what we have. And then we want to go to a velocity graph. We want to go to this one. So that means we're going to take the slope at each point. So from 0 to 5 seconds, so from 0 to 5 seconds here, it looks like its slope, so take 2 points on here. Let's choose this one and this one. So at this point, I'm going to call 0, 0. At this point, I'm going to call 5, 5. And the slope is y2 minus y1 over x2 minus x1. So that's y2 minus y1 over x2 minus x1, which becomes, when I plug it in, 5 minus 0 over 5 minus 0, which is equal to 5 over 5, which is equal to 1 meters per second. So that means for the first 5 seconds, this ladybug was only moving 1 meter per second. So I'm going to go ahead and input my 1, 2, 3, 4, 5, 6. So that means for the first 5 seconds, so 1, 2, 3, 4, 5 seconds, it was moving at 1 meter per second. So at every point, it was just going 1. So it starts like that. And then what about this region right here? We can tell just by looking at it that this is where it was chilling. So it was stopped, which means the velocity is 0 meters per second. So now I need to drop this down, and its velocity was 0 until 10 seconds. So 6, 7, 8, 9, 10, and it would be at 0. Like that. And then it started to move backwards. So we know this one's going to be a negative velocity. So this is backwards. So let's choose 2 points on this line now. So I'm going to choose this point here, and I'll choose this point here. So this one is 10, 5, and 12, 1. So let's do y2 minus y1 over x2 minus x1 now that I have my points. And you can go ahead and pause the video and do this on your own if you desire. It becomes 1 minus 5 over 12 minus 10, which is 1 minus 5 is negative 4 over 2, which is negative 2 ms. So now it actually is going to dip below and be negative. So I'm going to go like this and go 1, 2. This is negative 2 right here. And its velocity was negative 2 for this last little bit. Drop down, and it's negative 2 like that. Until it gets to, for the rest of the time actually, that we can see. So this is what our velocity time graph would look like if I zoomed in. So this means it was moving forward. It's a little bit fat. And then it was stopped. And then it was moving backwards. Like that. Alright, this question asks us to draw the velocity time graph and the acceleration time graph of Humpty Dumpty when he fell off the wall. So here's Humpty Dumpty. He's fallen down this wall. He's going to hit the floor down here. And we all know it's not going to be pretty. So what are some things we know about this? Well, the only thing we really know is that his acceleration is going to be the same as gravity, g, which is negative 9.8 meters per second squared. But what do we know about this? Negative 9.8. What does that do with any graph? Well, again, if we look at our a, v, x diagram, and we look at this side for slope, we know the slope of a velocity time graph is our acceleration. So that means we can draw two things. So the first thing that I'm going to add into this is going to be this graph here. Alright, so here's our graph. I'm going to zoom in. So we're going to say he fell off at time 0. So he started off at time 0. This is our velocity time graph. Velocity and time. So he started off up here. So his velocity was 0 and his time was 0. But then he starts to accelerate downwards, and again he accelerates downward at with a slope of negative 9.8. But I'm just going to round this to, this is approximately 10, negative 10 meters per second squared. So that means every second, so this is 1, 3, 5, 7, he's going to change his velocity by 10. So 10, 10 more, 10 more, 10 more, and 10 more. So this would be his velocity time graph. It's literally just a straight line. Alright, now that we have our velocity time graph here, we can make our acceleration time graph. But this is actually going to be really easy. So again, looking at our AVX diagram, AVX, we know that the slope of our velocity time graph is going to be our acceleration time graph. So the slope of this line, which we already know is negative 10, so slope equals negative 10 meters per second squared, is going to be our acceleration. And that's true at all time. So this acceleration, when something is falling, is going to be negative 10, or a little bit above that. Technically it's negative 9.8. Technically. We're rounding to 10. And it would just be a straight line right at negative 9.8, because gravity's acceleration on Earth does not change. So we're just going to plot that, and we are done.